The topic of percent composition, when I think of percentages, you probably do, is simply part over whole. Expressed as a percent means to multiply by 100. And really that's the same thing when we look at a formula. A chemical formula tells us two things. It tells us what elements are involved and how many of each. A percent composition really is saying how much does each of the different elements contribute to the mass of the entire compound. So percentage of each element in a compound by mass, part over whole, expressed as a percent. It can be determined from, the first, simply knowing the chemical formula of a compound. Taking the individual element's weight out of the entire compound's weight could be used to find a percentage. Secondly, it says we can determine a percent composition from a laboratory setting, an experimental mass analysis of our compound. So either from lab data or by simply looking at the formula of the compound are two ways that we can find percentages. Percentage may not always total to 100%, but we're going to come darn close, and that's simply just due to rounding. So it's close to 100% within a range of for accuracy. The percentage of part over whole expressed as a percent means to multiply or to slide your decimal over 2 for times 100. So if this example shows a compound C2Cl4F2, this is built of all nonmetals. It would be considered a molecule. It is not a binary molecular compound since it has 3 different elements. This actually looks like an organic compound, a whole different set of rules for naming organic compounds, so we won't entertain the name of this particular molecule. We'd like to know the mass percent of chlorine in the compound that contains 2 carbons, 4 chlorines, and 2 fluorines. Well, what we need to do is to consider how much chlorine contributes to the weight of the entire compound. 4 chlorines contributing to the weight of our entire compound will give us the percent by mass of chlorine. So the conceptual plan would simply show how we go about locating the mass of 4 chlorines over the entire mass of our compound. Go to the periodic table and let's start looking up some weights. Chlorine, number 17, do you see it on your chart? It has an atomic mass of 35.45. There's 4 of them, so we'll need to take that times 4. Now the molar mass of our entire compound, we have to add the mass of 2 carbons plus 4 chlorines plus 2 more fluorines. So 4 units of chlorine, each at 35.45, gives us the weight of 4 chlorines, 141.8. Now add 2 carbons, 4 chlorines, and 2 fluorines. Again, one at a time you find these elements off the periodic table. Carbon, 12.01. There's 2 of them. Chlorine, again, 35.45 times 4. And when you find fluorine, its atomic mass of 19.00. The sum of 2 carbons, 4 chlorine, and 2 fluorine is found as 203.8. The mass percentage of chlorine, its contribution to the total weight of the compound. 4 chlorines on the top at a weight of 141.8 divided by the whole formula, 203.8 times 100. The mass percentage of chlorine in our compound, 69.58%. Does your answer make sense? Well, because the percentage is less than 100 and chlorine is much heavier, we can see that that number makes sense. So when I ask to find a percent by mass of an individual element, its weight, its contribution to the total weight is said to be its percent by mass. If we find a formula, just given a straight formula as in this example, we simply add the weights and take part over whole. What if we determine mass composition of the following from an example where data is given? Calcium chloride. Here we did the hard part for you. If calcium on the chart, 40.08, Chlorine is 35.45, so they're just doing legwork in this slide and providing you the atomic weights, just saving you a quick minute so you don't have to spend time looking them up. What would the percent by mass for calcium chloride? Well, if I see two different elements, we would go and find a mass percent of calcium and a mass percent of chlorine. The mass percentage of calcium, its weight over the total weight, and the mass percentage of chlorine would be its weight over the total. So part over whole, and we will have two separate answers simply because we have two different elements in our compound. So if calcium, its formula weight was given to us as 40.08, and the mass of two chlorines is given to us as 35.45 doubled, the mass percentage of calcium can be written as 40.08 grams over 110.98 grams part over whole expressed as a percent. We find 36.11% by mass calcium. Same strategy for chlorine, 70.90 grams divided by 110.98, that's part over whole. Chlorine's contribution to the total weight of the compound is 63.88%. And double check, it's 36.11 plus 63.88, darn close to 100% of the mass. It certainly is, and a little bit off just by rounding. We can also use mass percent as a conversion factor. If the mass percent tells us the very definition of percent means parts out of 100 parts, you get the mass of each element in 100 grams of the compound. The fact that CCl2, F2, we found it to be 58.64% by mass chlorine means that if I had 100 grams of the sample, that's what the percent sign means, parts out of 100. 58.64 of those grams are coming from chlorine. So percent tells us parts out of 100 grams. That can be used as a conversion factor. In 100 grams of our sample, 58.64 of those grams come from the element chlorine. We're then able to calculate any other mass using that conversion. If I had 10 grams, how many would I have of chlorine? Just by setting up a conversion of part over whole. The grams of chlorine per 100 grams could identify grams of chlorine or grams of compound just by setting up a conversion factor, canceling the units desired. So let's see what I mean with an example. Find the mass of table salt that contains 2.4 grams of NaCl. Now, table salt is a common name for a compound. Perhaps you know, perhaps we don't. We're just beginning chemists here. Sodium chloride is the name for table salt. If we're given 2.4 grams of sodium, and the formula NaCl is for table salt, we first go to work and find the percent by mass of sodium in sodium chloride, part over whole. That's where the 39% came from. If sodium has an atomic weight of 22.99, chlorine has an atomic I'm sorry. Chlorine has an atomic weight of 35.45. The sum of sodium chloride, the total weight of our compound, would give us the mass percentage of sodium of 39%. We want to change the grams of sodium into grams of sodium chloride. When we found the mass percentage of sodium by taking Na over NaCl, we found its mass to be 39% contribution of sodium. Well, what that means is there's 39 grams of sodium and 100 grams of our compound, part over whole. Well, we can simply think about converting units. Given, and here's the given, 2.4 grams of Na. We want grams of Na to cancel, and we want NaCl grams. Think about just a simple dimensional analysis, and that's just fancy for saying units cancel. What do you want over what you are given? Want over given is dimensional analysis where we cancel units. We want NaCl given grams of Na. We want the grams of Na to cancel, it gets placed on the bottom. The mass percentage of 39% by mass Na tells us 100 grams of NaCl set over 39 grams of Na. If we had 6.2 grams of sodium chloride, out of that 6.2 grams of our table salt, 2.4 of those grams would be sodium. And of course, the other missing mass would be coming from the chlorine. Using percent by mass as a conversion factor, simply canceling units using that percent sign as its definition of parts out of 100 parts. Benzaldehyde is an organic name. Benzaldehyde is 79.2% by mass carbon. What mass of benzaldehyde contains 19.8 grams of carbon? Now, I would not expect you to know the formula of benzaldehyde. It will be given to us. Benzaldehyde is an organic compound. In this formula, benzaldehyde, you would be told that it contains 79.2% by mass carbon. That is a given quantity. Alrighty. So converting grams of benzaldehyde, that's the whole compound, and 79.2% by mass of it's coming from carbon. So the vast majority of its weight is carbon and has some hydrogens in it and an oxygen in it as well. But again, we don't need the formula. All we need to know is the mass percent of carbon in a larger compound. So we know if we had 100 grams of our compound, 79.2 of those grams would be coming from the carbon atom. Its contribution to the weight of the whole thing. Thinking about canceling units, what do you want set over what you are given? We want the grams of our compound given the grams of carbon. See how units of carbon grams cancel when it's placed on the bottom. Key sequence here is simply looking at 19.8 times 100 divided by 79.2. Canceling the grams of carbon transfers grams of carbon into grams of our compound called benzaldehyde. And they're writing the word out because knowing the formula is not necessary to do this calculation. The mass of benzaldehyde is more than the mass of carbon, so that number did make sense. Now, in conversion factors from chemical formulas, these chemical formulas have inherent in them relationships between the number of atoms and the number of molecules, or moles of atoms and moles of molecule on a macroscopic scale. And those relationships can be used to convert between amounts of the constituent elements and the molecules, simply like a percent composition. Let's make sense of that a little bit more by examining some examples. Find the mass of hydrogen in 1.00 gallons of water. I need to cough. I apologize. I'm fighting this head cold still. Now, a couple of things I wouldn't know that I'd have to go to my Google or my chemistry book and look up some conversions in the back. What's the mass of a gallon of water? Well, assuming that we know water has a density of 1 gram is the same as 1 mil, I'm really being asked how many milliliters comprise a gallon. Well, a gallon of water to a liter of water to a milliliter of water is the weight of our water. A lot of conversions here with just simple dimensional analysis. Alrighty, so the relationships that I would have to Google, I wouldn't know this. Perhaps there's conversions right in the back of our chemistry book, but Google search engine far outweighs this in quickness. I would type in how many liters is equal to 1 gallon. Just a quick Google search showed us 3.785 liters is the same as saying 1 gallon. I would never expect you to know that off the top of your head. I didn't. I'd have to, like I said, I Googled it. But now that I know that conversion, the liter unit to a gallon, again, I'm going from the common American unit gallon to a metric unit, a liter. We also know that 1 gram is 1 mil, so we have to do a little conversion with the liters into a milliliter. So 3.785 liters, slide the decimal 3 spots to the right, is 3,785 milliliters. And now that I know the density of water is 1, 3,785 milliliters is exactly the same number of grams. Now I'm ready to go. Grams to mils and onto the mole. So we know, just to kind of write down what we had said, 1 gallon is equivalent to saying 3.785 liters. In every 1 liter, there is 1,000 milliliters. So to convert, we would cancel the liter. I just simply slid my decimal 3 spots to the right, and you get a larger number, 3,785. Now in scientific notation, 3.785 times 10 to the third grams is exactly the same as saying 3,785. So that's all I did. 3.785 times 1,000 is indeed the number of grams of water. Now I'm just doing a mole map problem. If I know the mass of water, 3,785 grams, I'm going to simply use the molar mass to convert it to a mole. 2 H's and an O added together off our periodic table, the weight of H2O's formula weight. 2 H's added to an O is 18.02 grams. How many hydrogens in the water formula? See that subscript of 2? Tells me there's 2 moles of hydrogen contained in every 1 formula of water. So 2 over 1 tells me there's twice as many H's in every water molecule. And the 1.008 grams is the atomic weight of hydrogen, telling us out of the 3,785 grams of water, hydrogen is contributing 423 of those grams. 4.23 times 10 squared is the same thing as saying, that's written in scientific notation, but that's the same as saying 423 grams. If you don't like scientific notation, it's just as easy. Those numbers aren't that large. So 3,785 grams of water is the same as saying a gallon of water. And in that gallon of water, we would have 423 grams of hydrogen. I really don't like converting between the English and metric system that often. This is not an example I would ever put on a test. I don't know those conversions by heart just simply because we don't do them often enough. But nonetheless, it was a good mental exercise. Got us our little Google search there. Here's a practice. How many grams of sodium are in 6.2 grams of sodium chloride? This one's a little easier. I think we don't need any of those conversions. Part over 100 parts. So if we are looking at 6.2 grams of sodium chloride and we want to know how much sodium we have, we're going to use the percent by mass as a conversion. The given amount is the 6.2 grams of sodium chloride. That's table salt. And what we'd like to know is out of those 6.2 grams, how many of them are coming just from sodium? So the conceptual plan would show us we need to convert grams of NaCl into moles of NaCl, into moles of Na, back into grams. Here's some relationships that will allow us to convert. The molar mass of our table salt, 1 Na added to a Cl, we get 58.44 grams. So that's just simply saying the formula weight. So if 1 mole of table salt is 58.44 grams, 1 mole of sodium, its weight off the chart, 22.99 grams. So we just go to work converting from what we want, starting from given, working toward what we want. Notice in our formula we have a 1-to-1 mole ratio. Looking at the formula, there's 1 Na in the formula of NaCl. So start by writing 6.2 grams NaCl. We want to cancel the gram unit and head into the mole. 1 mole of sodium chloride with its formula weight of 58.44 grams cancels the gram unit. We mentioned there's 1 mole of Na for every 1 mole of NaCl. That's just showing us the subscript of sodium is 1 in our formula. Now to convert from moles of Na back out to grams, we multiply by the molar mass of Na, 22.99 grams right off of our periodic table. On your calculator, hit it with me, double check your key sequence. I'd simply say 6.2 divided by 58.44 times 22.99. That's going to give us a mass of 2.4 grams of sodium. In our sample of table salt of 6.2 grams, 2.4 of those are coming from the element sodium. Part over whole times 6.2. That's all we've done. The mass of sodium is over the mass of the entire structure. Part over whole times the given amount. Here's a term that's coming back from the earlier parts of our lesson, an empirical formula. We defined earlier the simplest whole number ratio of the atoms of elements in a compound. In other words, it's a formula whose subscripts cannot be reduced down any further. They're in the lowest subscript ratio possible. And I remember saying it may or may not match its molecular formula, which we called its true formula. If we have data, percent composition data of each element in a compound, we can actually calculate its empirical formula. Knowing each element's contribution to the weight of the entire compound allows us to calculate an empirical formula. So a couple of ways we can determine from elemental analysis. If we know the masses of the elements formed when a compound decomposes, or that's a decomposition pattern, reacting together in a combination pattern. Or we can do a combustion analysis, or simply know percent composition. Given some data, we can follow several different examples of how we can use this data to calculate an empirical formula. So when we find an empirical formula, the lowest subscript ratio possible, step 1 says we have to find the grams for each of the elements, knowing their percentages. But the easiest way to do that is just assume you have 100 grams of the compound and percents are directly the gram units. If they give us different amounts other than for a percent sign, just use the gram provided. But if they give you percents, just assume 100 grams and then your percent signs change to grams immediately. Step 2, once we know the percentages converted to grams, we do a mole map problem and we convert grams to moles. See, subscripts are mole ratios, not grams, but mole ratios. Percentages are by mass, subscripts are by moles. So we do a mole map problem and we convert our mass into moles by using the atomic weights. We write a pseudo formula using moles as subscripts, and I say pseudo because these are going to typically be decimals. They are not going to come out as whole numbers, and we know that subscripts must come out as whole number ratios. So when we say we write a pseudo formula, we write down what we know so far and then show some steps of how to convert that into a whole number. That trick of converting these decimals into a whole number says skim the list, the entire list of all the numbers you've generated so far, and find the smallest number. I don't care how many elements are in the compound, go through the list of moles you've converted and find the smallest number. If the result is within 0.1 of a whole number, you're allowed to round, and that's just due to experimental data. We can round a little bit, but we don't want to round too far or we'll come up with a wrong answer. So general rule is 0.1 of a whole number, you're allowed to round it down or round it into that whole number. But otherwise, when we divide through by the smallest number, typically they're going to work out to be a whole number ratio. Once in a while, even if we divide through by the smallest number, we may find a decimal remaining. What if we end up with a 0.5? After we've divided through by the smallest number, I still have a decimal, and that decimal is a 0.5. Now think of that as a 1/2. What would I multiply a 0.5 by to get rid of that decimal? Well, you're going to double it. Everything needs to get doubled, not just the 0.5, but you keep the ratios the same. What you do to one answer, you do to them all. So if one of them ends with a 0.5, multiply all of them by 2. If you see a 0.333, that's a third, so you're going to triple it. Even if you get 0.67, that's 2/3, you're going to triple it. 0.25 is a quarter, so you'll multiply by 4, etc. Typically, I'm going to tell you 90% of the time, they're going to come out as whole numbers once you divide through by the smallest one. In a rare instance, if you still get a decimal, that decimal is representing a fraction, and you can multiply that fraction out by some alternate method. Laboratory analysis of aspirin determined the following mass percentage. C, the element carbon, contributes 60% of the mass of an aspirin molecule. Hydrogen contributes 4.48, and oxygen's contribution of 35.53% by mass. Notice the total, close to 100%. Given percent composition, we want to write down a formula. So C something, H something, O something, where those somethings are called subscripts. And those subscripts are low whole number mole ratios. Percent sign stand for grams. Subscripts stand for moles. Let's assume we have a 100-gram sample. That's the easiest, because in 100 grams, we now know how many grams of each element we have. So working through to find the empirical formula given mass percentage. Assume a 100-gram sample and write down for each element how many grams we have. 60% by mass carbon, 4.48% by mass hydrogen, 35.53% by mass oxygen. Interpret, that tells us in 100 grams of aspirin, there's 60 grams of carbon, 4.84 grams of H, and 35.53 grams of O, oxygen. Step 1, percent signs turn to grams. Easy enough. Assuming a 100-gram sample, that's the easy step. Change percent signs to grams. Now we do mole map work. If we know the number of grams, and we do, and want to convert into a mole, it's just a mole map problem using atomic weight. Now remember, ultimately we're trying to find subscripts. C something, H something, O something, where those little subscripts are mole numbers, and they must be whole number ratios. What we know is the carbon is 60 grams, the hydrogen 4.48, and the oxygen 35.53 grams. We have 3 separate mole problems converting each element into a mole unit. So that's not so tough. Take the grams and divide each by its atomic weight, and then you have a mole. I mean, check out your mole map, that test-taking tool page that you've printed off from your Blackboard site. The scale at the bottom left heading into the mole, you literally trip over the conversion factor. It says a molar mass, the weight of the element off of the chart. So let's do that. Take a moment and hit each one of the grams, divide by its atomic weight, and convert into moles, and record what you find. Thanks for your patience as I struggle through this cold. All right, so here we go, going to work for mole conversions. Do you find carbon's atomic weight? 12.01 grams. Find hydrogen's atomic weight, and you'll see it 1.001 or 1.008. And oxygen, of course, at 16. We want to convert each of those gram units into mole units by a simple divide by. So here we go to work calculating the moles. 60 grams of carbon divided by its atomic weight of 12.01 tells us we have 4.996 moles of carbon. We want the mole given grams. We divide by atomic mass to convert mass into mole. Heading into the mole is always divide by. Heading out of the mole is always a multiply by. Do the same strategy for hydrogen. 4.48 grams divide by 1.008 grams. We cancel the gram units and find 4.44 moles of H. One more element to do, turning grams of oxygen into moles of oxygen. 35.53 grams of O times 1 over 16 tells us 2.220 moles of oxygen. So far our journey, kind of summarizing. Step 1, percent sign change to grams. Step 2, grams get converted to moles. And that's simply dividing by each element's atomic weight. However many elements there are in our formula in the list provided, same strategy, grams divided by atomic weight. And now we have the beginnings of our mole number. We're not done yet because I don't see perfectly whole number ratios. So far, we have what's called a pseudo formula. The pseudo formula says, here's the ratio, and we have to keep that intact. The ratio is C, 4.996, H, 4.44, O, 2.22. So those decimal places have to get converted back into a whole number ratio. Oh, that went by too fast. Let me see if I can back up. Now I hit back up. Oh, patience, please. Here we go. 4.996, 4.44, 2.22. Alrighty, that ratio must be kept the same. I can't just round them away. So what was our strategy? Out of that list, what's the smallest number? 4.996 compared to 4.44 compared to 2.20. You got it. Oxygen's number is the smallest. We're going to take each one of the elements and divide it by the smallest number. See what we get. Don't round at this point, but divide by the smallest number. Let's see what we come up with when we divide through by oxygen's value of 2.22. Carbon worked out to 2.25. Hydrogen is exactly twice that of oxygen. Now that we've divided through by the smallest number, I still have a decimal. Now again, this is rare, but I tried to find an example where we would have a situation to consider. 90% of the time, this step ends this journey. We've got whole numbers, presto, we've got a formula. But here's an example I worked through, and now we still have a decimal remaining. 0.25 is a fraction. It's a quarter, 1/4. We'll need to multiply all of the subscripts by 4 to get rid of the 0.25. What do we get if we multiply the entire list of subscripts by 4? Whatever factor is going to give us a whole number. If our fraction was 0.25, that's a quarter, so we're going to multiply through by 4. We had said if it comes out with a half, you're going to double it. Comes out as a third, you're going to triple it. So this one came out as a quarter. 2.25 times 4 gives us a subscript of 9. 2 times 4 gives us a subscript of 8. And oxygen comes out as a value of 4. Aspirin's empirical formula, C9H8O4, the lowest subscript ratio possible. And friends, the beautiful thing about this, I can double check my work. If I take each element and just take part over whole, the weight of 9 carbons out of the weight of a whole aspirin, I believe is 180 if I calculated that, part over whole, I'm going to find it to be 60% by mass of carbon. 8 hydrogens, 8 over 180 is going to give me 4.48 grams or 4.48% hydrogen. So there is a way to check this to make sure your subscripts do indeed match the given percent by mass composition. An empirical formula, the lowest subscript ratio possible. Step 1, percent sign changed to grams. Step 2, grams get converted to moles. Step 3, divide through the list of moles by the smallest number and work them into a whole number ratio. Those become the subscripts with which we write our chemical formula. Try one on your own. See if you would come up with the same answer. We'd like to determine an empirical formula for stannous fluoride. Now that's tin 2 fluoride. It contains, oh dear, I'm going to pause here and get my screen back up. You try this example and I'll get this fixed and come back again in a moment.